Let's move on to discuss on the attainment of equilibrium in chemical reactions. Here is the index. I am going to talk about the attainment of equilibrium in chemical reactions. The relationship between Kp and Kc. We are going to talk about the case 1, case 2 and case 3. The dependence of dissociation constant with the formation equilibrium constant. These areas we are going to look into. So chemical reactions are nothing but how the reactants mixed up to form the products. Followed by I am going to talk about the relationship between Kp and Kc. Attainment of equilibrium in chemical reactions. A chemical reaction in equilibrium involves the opposing reactions. One of the reactions produces the product and is known as forward reaction, while the other produces the reactants from products and is known as reverse reaction. Let's discuss on the chemical equilibrium. As you know, the rate of forward reaction is equal to rate of the reverse reaction. That's referred to as chemical equilibrium. So I got the reactants and the reactants mix up to form the product at one stage. So what is the rate of forward? And similarly the products will become the reactants at one stage. That's referred to as rate of reverse reaction. I got nitrogen and hydrogen, N2 and H2 will form ammonia, NH3. Over here, ammonia at one stage becomes the products. So as I indicated, the both are equal and this is dynamic. If it is lesser, automatically this will occur, and if this is lesser, automatically this will occur. So both the things will be happening at a short. That's referred to as chemical equilibrium. So this is indicated by a chart of containing time versus concentration. You are able to see A and B. A and B is the reactants. It started reducing at one stage and it's reducing, and you are able to see the products is coming into picture. So once the reactants and products become equilibrium at one stage, that's referred to as equilibrium position. Is the reactants and products. So chemical equilibrium is dynamic in nature. At equilibrium, the reactants and products both are present in the reaction mixture in definite amounts. The equilibrium concentration of the reactants and products do not change under constant temperature, pressure and catalyst. I want to show a 3D of how the chemical reactions, constant temperature and closed system is happening in the equilibrium position. As indicated, the rate of forward reaction is really equal to the rate of reverse reaction. This is referred to as dynamic equilibrium. I got a water towel. Now let's talk about the evaporation. You are able to see the water molecules are coming out. The liquid became gaseous. The water molecules are gone. So it's an open system because it's in the air. Now I got a closed system now. Into the closed system I am trying to evaporate. If I am trying to evaporate, automatically the water is coming out, but still it's getting settled once again. So the condensation is happening. Both evaporation and condensation is happening at a shot. So it's become an equilibrium. The liquid is converted to gas and gas is once again converted to liquid. This is how an equilibrium is maintained. Consider a general equilibrium reaction at constant temperature is represented as A into A plus B into B. So this is the reactants. So reaction constants C plus D, the reactants and products. According to the law of mass action, the rate of the forward reaction is Rf is equal to Kf into A power A into B power B. And the rate of the reverse reaction is given by Rr is equal to Kr C power C D power D, where Kf is the rate constant of the forward reaction and Kr is the rate constant of the reverse reaction. At equilibrium, Rf is equal to Rr. So Rf is equal to Kf into A power A into B power B. Rr is equal to K power Kr C power C into D power D. So at equilibrium, the forward reaction is equal to the reverse reaction. So Kf divided by Kr is equal to C power C D power D divided by A power A into B power B. So Kc, equilibrium constant, is equal to forward divided by the reverse reaction constants. So Kc is equal to C power C D power D divided by A power A into B power B. This equation of Kc is also known as equilibrium law of equation. So Kc is the equilibrium constant expressed in terms of molar concentration of reactants and products. For reactions involving gaseous reactants or products or both, it is more convenient to use partial pressures instead of molar concentrations. Thus, Kc in equilibrium law equation becomes Kp, which is the equilibrium constant expressed in terms of partial pressure.